Hello, dear students. I am Samir Velankar and I welcome all of you to this video, which is based on the topic All Pair Shortest Path of a Graph. It is also called as Floyd-Warshall's algorithm, as named after its creator. Now, I have a graph over here which is having four vertices and some edges. I think 1, 2, 3, 4, 5, 6. Six edges are there in this graph, and it is a weighted directed graph. Every edge is having direction and every edge is having weight. So it is weighted directed graph. Now this graph is stored in the computer memory in the form of cost matrix. Now we know that graph is usually stored in the form of adjacency matrix, but we are not going to store this graph in the form of adjacency matrix, but we will be using cost matrix. Now there are few rules for cost matrix. Now C is the cost matrix here. Obviously it will have V rows and V columns, where V are the number of vertices. So in this graph there are four vertices. So we have a cost matrix C which is having four rows and four columns. Let's see the rules for creating this cost matrix C. Now the rules are that if two vertices U and V, imagine U and V are two vertices, if they are adjacent, I mean there is an edge from U to V, then U row and V column, that is CUV, will not be equal to 0, and we will store the weight of that edge in that particular element. As an example, you just check that there is an edge from 1 to 4. 1 to 4, there is an edge with a weight of 4. So, in the matrix, row 1 and column 4 is going to store 4. I hope you are observing it. So, if U is having an edge to vertex V, U to V there is an edge, then in U row and V column we will store the weight. This is the first rule. The second rule is CUV will be equal to 0 if U is equal to V. That means for diagonal elements we are simply going to store 0. So as you can see in the matrix, C11, C22, C33 and C44, all these diagonal elements are 0. And now the major point, the biggest point over here is CUV, U row and V column, is set to infinity, very large value, if vertex U is not adjacent to vertex V. So as you can see in this graph, vertex 3 does not have directed edge to vertex 2. Observe this. Vertex 3 is not having an edge to vertex 2. In fact, 2 is having an edge towards 3, but 3 does not have an edge towards 2. Hence, row 3 and column 2 will be set to infinity. I repeat, if vertex U is not having a directed edge towards vertex V, then U row and V column will be set to infinity. This is how the cost matrix is made. Now, why am I talking so much about this representation? Please try to understand. Is because we have been storing graph in the form of adjacency matrix. Let's call the adjacency matrix as G. Now, for the above graph drawn, this matrix will be again 4 by 4, 4 rows and 4 columns, because there are 4 vertices in our graph. Now, what are the rules for filling adjacency matrix? The rule is, if vertex U is having an edge to vertex V, then store the weight. Otherwise, if vertex U is not having an edge to vertex V, then store 0. Like, what will be the entry 1 1? First row, first column, it will be 0, because vertex 1 is not having an edge to vertex 1. 1 is not adjacent to 1. I hope you remember what do you mean by adjacent. U is adjacent to V if U is having an edge towards V, but there is no edge from 1 to 1. So 1 1 entry will be 0 in the adjacency matrix. Let's fill other entries in the matrix just for comparison. 1 to 2 will be 2. You observe there is an edge from 1 to 2 and the weight is 2. 1 to 3 is 0. Now that's the big difference, you see. 1 to 3 is 0 because there is no edge from 1 to 3. So in the adjacency matrix, 1 to 3 is going to be 0. But in the cost matrix, 1 to 3, row 1 and column 3 is going to be infinity. Because if U does not have an edge to V, then U comma V is set to infinity in the cost matrix. Why are we doing this for the cost matrix? Please try to understand. Cost matrix is showing cost of going from vertex U to vertex V. Now you tell me, for some time you imagine that vertex 2 does not have an edge to vertex 3. Imagine this. It does not have a directed edge towards 3. And if you are asked, what is the cost of going from 2 to 3? Now your answer should be they are not connected. Directly they are not connected, isn't it? So the cost has to be infinity. Yes, the cost of going from 2 to 3 is infinity right now. So row 2 and column 3 of the cost matrix should be stored as infinity. Yes, I fully agree that there can be another path from 2 to 3. Maybe 2 has a directed edge to 1 with a weight 2 and 1 has a directed edge towards 3 with a weight 3. Then actually 2 to 3 is possible. 2 to 3 is possible via 1. And the cost will be 5 actually. 2 plus 3 5. You can reach from 2 to 3 via 1. But there is no direct edge at the moment. You should say at the moment that 2 and 3 are infinitely away. I hope you are understanding notation of the cost matrix and notation of the adjacency matrix. Adjacency matrix will define neighborhood and cost matrix will define cost needed to reach from vertex U to vertex V. Let's fill the adjacency matrix just for filling sake. What will be 1 to 4? Observe the graph. 1 and 4. Cost is 4. You can go from 1 to 4. 2 to 1? No, there is no edge from 2 to 1. So it will be 0. 2 to 1 is 0. But in the cost matrix, 2 to 1 will be infinity as there is no edge from 2 to 1. 2 to 2 is 0 obviously because there is no edge from 2 to 2. 2 to 3 is 3. Observe there is a directed edge from 2 to 3 and 2 to 4 is 0. Similarly 3 to 1. 3 to 1 there is an edge. So cost is 8 or rather weight is 8. 3 to 2 there is no edge. So 0. 3 to 3 is 0. 3 is not adjacent to 3. 3 to 4 is 0. 4 to 1 is 6. 4 to 2 is 0. 4 is not adjacent to 2. And 4 to 3 is 20 and 4 to 4 is 0. That's adjacency matrix and you should compare it with the cost matrix. Isn't it? Let's revise this very quickly. Very fast we'll revise. Suppose I am having some arbitrary graph. I am drawing some graph, okay? Even I don't know what I am drawing. But imagine some graph like this. Now this graph again is having 4 vertices and I am showing some weights. Weights for all the edges. Now what is going to be the cost matrix for this? The cost matrix is again going to be 4 rows and 4 columns. And the entries will be 1 1 will be 0 because cost of going from vertex 1 to vertex 1 is 0. Come on, if you are at vertex 1, you are at vertex 1. You don't have to travel at all. That is why all the diagonal elements 2 2, 3 3, 4 4 are 0 in the cost matrix. But 1 to 2 as you see in the graph is 2, 1 to 3 is 3, 1 to 4 should be infinity because there is no edge from 1 to 4. 2 to 1 is infinity again, 2 to 2 is 0, 2 to 3 is infinity, there is no edge from 2 to 3 and 2 to 4 is 10. 3 to 1 is infinity, 3 to 2 is 10, 3 to 3 is 0, diagonal element and 3 to 4 is 5. Finally, 4 to 1 is infinity, no edge from 4 to 1. 4 to 2 is infinity, 4 to 3 is infinity, and 4 to 4 is 0. That's the cost matrix C for the given graph. I hope you follow it, isn't it? So now coming back, once you have understood what is this cost matrix and what do you mean by representing a graph using a cost matrix, now our aim is, I'll just erase this adjacency matrix, give me some time. Now our aim is we want to find all pair shortest path. What it means is we want to find shortest distance from every vertex to every other vertex. So what are the answers we want? What is the shortest distance from 1 to 1 we would like to know? Very silly, isn't it? Shortest distance from 1 to 1 is 0. Come on. If you are at 1, you are at 1. You don't have to travel. But then we want to find shortest distance from 1 to 2, shortest distance from 1 to 3, from 1 to 4. But that's not all. We want shortest distance from 2 to 1, 2 to 2, 2 to 3, and 2 to 4. And this goes on, and we want shortest distance from 4 to 4, up to 4 to 4. If you count, we want 16 answers. For a 4 vertex graph, we want 16 answers. 1 to 1 up to 1 to 4, 2 to 1 up to 2 to 4, 3 to 1 up to 3 to 4, and 4 to 1 up to 4 to 4. We want 16 answers. Now observe the cost matrix again. This is the fun part. This cost matrix exactly has 16 elements. For each pair of vertex, there is an element in this cost matrix. So when we will run our all pair algorithm, as I have written here, I am marking it. This algorithm, is going to compute the shortest distance between every vertex to every other vertex. So by the way, when this algorithm all pair shortest path will end, we have not yet executed it, but imagine that we have executed it and this algorithm ends, then all the entries in this cost matrix, that is C matrix, will give shortest distance from vertex U to vertex V. As an example, observe that there is no edge from 3 to 4. So entry 3 comma 4, I am marking it, is 0 here. Just check. It is, sorry, infinity. I'm so sorry. 3 to 4 is infinity, isn't it? Right now, 3 is infinitely away from 4. But if you observe the graph carefully, there is an edge from 3 to 1, correct? There is an edge from 3 to 1, and there is an edge from 1 to 4. So you can go from 3 to 4 via 1, and the total distance will be 8 plus 4, that is 12. So this entry infinity will be changed to 12 by our algorithm. All pair algorithm is going to change these all entries of C. If possible, it is going to change all the entries to the minimum value. And that's how matrix C will give us all pair shortest path. I'm not saying that there can be only one path from 3 to 4. There might be several paths from 3 to 4. I think in this graph, there is only one path from 3 to 4. I think so. 3 to 1 and 1 to 4. But if there are several paths from 3 to 4, all the paths will be checked by our algorithm and the minimum path, minimum distance will be taken and it will be stored in row 3, column 4. I hope you have understood what is the problem and what is the cost matrix. I really like this algorithm, by the way. This algorithm is so small, isn't it? Just 4 to 5 line algorithm. And it is going to do this all trick of finding all pair shortest path. But listen, its complexity is quite high. Time complexity is high. So we will learn how to run this algorithm, what happens when this algorithm operates, and how all pair shortest paths are found in the next video. Thank you very much.